Let's draw our electrons around fluorine. So we know that the order of filling shells is the first shell has 2 electrons, the second shell has 8 electrons, and the third shell also has 8 electrons. So we have 2 electrons on the first shell. Fluorine's in the second period, so we also have a second shell. This is going to be the valence shell because it's the outer electron shell, and it would have 7. So 1, 2, 3, 4, 5, 6, 7. Now, it has 7 electrons, and we also know, it has 9 electrons, 7 valence electrons, and we also know that fluorine, being the 9th atom on the periodic table, has 9 protons. It has 9 protons. The atomic mass is approximately 19. And if it has 9 protons, positive protons, then that means that it must also have 10 neutral neutrons. So this isn't an ion. This is a fluorine atom that is neutral. It doesn't have a charge, neither positive nor negative, because it has 9 positive protons, but then it also has 9 negative electrons. And so if it has 9 positive protons and 9 negative electrons, each proton has a positive 1 charge, each electron has a negative 1 charge. These charges are balanced, so they cancel each other out, and the resulting charge on this entire atom is neutral. But that changes depending on whether this atom gains or loses an electron. So it does happen in chemistry with atoms in chemical reactions. By bonding, an atom can either gain or lose electrons. And whether an atom gains or loses electrons depends on its chemical properties and where it is on the periodic table, because the periodic trends will determine whether atoms like to pull electrons or like to get rid of electrons. So let's talk about an ion of fluorine. And we'll discuss this shortly, but fluorine likes to gain electrons. And so if we were to add an electron to fluorine, so if fluorine were to gain an electron from elsewhere, and it would usually gain an electron from another atom, but it would gain an electron from elsewhere. Now, fluorine doesn't have 9 positive protons and 9 electrons. It has 9 positive protons and 10 negative electrons. So it actually has a net negative 1 charge, because the 9 protons here are canceled out by the 9 electrons here, but then there's 1 extra electron. There's the 9 electrons required to cancel out the proton charges, but then there's 1 extra electron. And that extra electron is going to give this atom a net negative 1 charge. So what we would say is this atom has a charge of 1 negative. It works the other way too. If we have an atom of lithium, or let's talk about beryllium. If we have an atom of beryllium, beryllium is right here. So beryllium is in group 2, so it has 2 valence electrons. It is in the second period, so it still has 2 electron shells. So we have beryllium, we'll draw its first shell, and we know that the first shell always contains 2 electrons, and then I'll draw its second shell out here. And its second shell, it being the second group, beryllium is the 4th atom on the periodic table. So it has 4 electrons total, 2 of them on the inner shell and 2 of them on the outer valence shell. Beryllium, unlike fluorine, likes to lose electrons. So while this is balanced, what it may end up doing, and what it tends to always do, is it likes to get rid of an electron and give it to somebody else. So it will give an electron to another atom, which means it no longer has 4 positive protons and 4 electrons as a neutral atom. It has lost one of its electrons. So let's actually indicate beryllium has 4 protons that are positive. Beryllium has an atomic mass of 9, which means I also have 5 neutrons. It no longer have 4 protons and 4 electrons. I've lost 1 electron. I only now have 3 electrons, And so I have one extra positive charge. The three negative charges here are canceled out by three of the protons, but then I have one extra proton. So we would say that this atom has a net charge of +1. And we like to put the positive symbol after the number, unlike in mathematics where it's also an operator, we put it in front. In chemistry, we like to put it after the symbol. So I have two types of atoms. This is a negative atom. This is a negative ion. This is a positive ion. We do, of course, have special names for these types of ions. If an atom is a negative ion, we call it a anion. And if an atom is a positive ion, we call it a cation. And the way to remember this is the word cation itself has a T in it, which kind of looks like a plus, the plus of the positive charge. And anion has an N, which stands for negative. So we have anions and cations. So now we know what an ion is. Let's discuss what types of atoms tend to become what types of ions. And in order to discuss that, we have to talk about the octet rule. So let's move down to our periodic table and let's discuss the tendency for atoms to have a full valence shell. Atoms are really only at their happiest when they have a full valence shell. And we know that the very first shell has a total of 2 electrons, the second shell has a total of 8 electrons, and the third shell has a total of 8 electrons as well. So an atom is only happy when its outside shell is full. So if the atom has 1 shell, it wants 2 electrons in it. If it has 2 shells, it wants 8 electrons in its outer shell. If it has 3, it wants 8 in that one. So that means if I am fluorine, or let's take chlorine as a different example. If I have chlorine, so chlorine is in the third period, so it's got 3 orbitals, it's got 3 shells, and it's in the 7th, 1, 2, 3, 4, 5, 6, 7. It's really the 17th group, but we've got 7 valence electrons in chlorine. So let's draw the Lewis dot diagram for chlorine. So I got chlorine here, and I have 1, 2, 3, 4, 5, 6, 7 electrons. 1, 2, 3, 4, 5, 6, 7. Well, that's the third shell. And in the third shell, which is its valence shell, the third shell likes to have 8 electrons in it. But if we look at chlorine, chlorine is missing an electron to have a full shell. This is the third shell because it's in the third period. Remember, every atom here has 1 shell, every atom here has 2, and every atom here has 3. It wants 8 electrons in that valence shell. It's not happy until it gets that 8th electron in its valence shell. And it's ravenous. It wants to get that electron from anyone it can, and it's going to get it from another electron. Because it's so close. It's so close to having a complete octet. It's so close to having a full valence shell. And the tendency of atoms to want 8 electrons in their shells, we call it the octet, which just means 8, the octet rule. So the octet rule says that electrons want to have a total of 8, atoms want to have a total of 8 electrons in their valence shell. Of course, like most things in chemistry, there are exceptions. Obviously, the first shell only has 2 electrons total, but for the majority of atoms, we're looking at gaining 8 total in their valence shell. So chlorine would either need to lose 7 electrons or gain 1 electron to get a full valence shell. And it's much easier to gain 1 electron than to lose 7. So chlorine's going to want to gain an electron. So chlorine tends to become more negative. So chlorine tends to become an anion when it becomes an ion because it tends to have a -1 charge. So as soon as it gains that extra electron, it now has a -1 charge. And that's the same trend for most of the atoms here. These atoms here are real close to having a full valence shell. All of the atoms in the halogen group are 1 electron away from having 8 electrons. They're 1 electron away from that octet rule. And all of the atoms in the 16th group are 2 electrons away from having a full valence shell. So these guys are really close. They're really close to completing their octet rule, and so they're pretty ravenous in stealing electrons from other people. Well, let's go all the way down here, and let's look at lithium. Lithium, let's draw its Lewis dot diagram. So this is its second shell is the valence shell, and it's only got 1 electron on that outer shell. It has 2 on the inner shell and then 1 on its outer shell. So here's a Lewis dot diagram. It's got 1 electron, and lithium would either need to gain 7 electrons to have a full valence shell, or the alternative is if lithium loses that outside electron. And let's actually now draw it as a Bohr Rutherford atom. So there's 2 on its inner shell, and it's got this outer shell where it's only got 1. The rule says an atom needs to have a full valence shell to be happy. But instead of gaining 7 electrons on this outside shell, if lithium were to just lose this 1 electron, there's no longer electrons on this valence shell, so this valence shell no longer exists. And if that valence shell no longer exists, that would make this inner shell the new valence shell. And if that's the new valence shell, it is full because it already has 2 valence electrons. So, a clever way to gain a full valence shell for these guys right here, for all of these left side atoms, for these group 1, group 2 alkali metal atoms, is to, instead of gaining 6 or 7 electrons, is to just lose the few electrons they have in their valence shell so that the inner shell, which is already full, becomes their full valence shell. And that's exactly what they do. So lithium tends to lose its electron. So it will lose its electron, give it to someone else, and it's left with 2 electrons. Now, lithium is the 3rd atom, so it has 3 protons. And if it has 3 protons, if it loses an electron, now it only has 2 electrons. And so if there's only 2 electrons and 3 protons, this has a net positive charge. So this is an ion, a positive ion. We would call this a cation. So lithium and all of the atoms in group 1 tend to become cations because they're electron losers. So let's generalize. These atoms over here are electron losers. So they lose electrons. And all these atoms over here are electron gainers. They're electron takers. They like to steal electrons because they only need 1 or 2 in order to get a full octet, whereas these guys only need to lose 1 or 2 in order to have a full octet underneath. So we have our cations, or atoms that tend to be cations, over here. We have our anions, or the atoms that tend to be anions, over here. But what about these guys right here? These are the noble gases. Well, let's draw one of the atoms for a noble gas. Let's talk about argon. So argon has 2 electrons in its inner shell. So argon is atom 18. So I know that it's going to have 18 protons. It's going to have 18 electrons, and it's got an atomic mass of 40. So if it's got an atomic mass of 40, 18 of that is protons, so then it must have 22 neutrons. So I have 18 electrons. So 1, 2 on this shell, and then I got a next shell, and I got 8 on this shell. So 1, 2, 3, 4, 5, 6, 7, 8. And then I have my third shell. So I have 10 right now. I need 18 total. So I'm going to put another 8. 1, 2, 3, 4, 5, 6, 7, 8. So argon has 8 electrons in its third shell or in its valence shell. That's as many as can fit. So it already has a full valence shell. It doesn't want to lose, it doesn't want to gain, because as soon as it does, it throws off its perfectly balanced shell. It's already happy. It's got all of the electrons it wants. So it doesn't need to gain nor lose. It doesn't need to become an anion. It doesn't need to become a cation. And that's why we call these the noble gases, because they're extremely stable. They do not like to react. They do not like to bond. They do not like to give electrons. They do not like to gain electrons. This whole row of atoms are the most stable atoms on the periodic table. They like to exist as themselves, and they do not like to be part of a molecule or compound of any kind. So these are extremely stable. They're extremely safe. And that's why we call them the noble gases. So electron losers over here. Electron takers right here. And our stable atoms right here. These tend to become, so let's use a clear periodic table here. Just to summarize, so we have the atoms that tend to become positive, so these are our cations. These are atoms that tend to be negative. So there are anions. And these are stable atoms. They don't like to bind at all. They're all very stable. So electron givers, electron takers. And I know what you're thinking. You're thinking, well, what about all the other atoms on the periodic table? And you're absolutely right. These ones over here will also tend to be electron takers. But as soon as we start getting into this area here, of course, like most things in chemistry, we're getting into the gray area where some of these are going to be electron givers, some of them are going to be electron takers. It depends. The tendency does tend to be, if they're more on the left, they tend to be more electron givers. If they're more on the right, they tend to be electron takers. But of course, there's exceptions to that rule. And we'll talk about all of that. But that'll wrap up today's lesson, and we'll discuss more about what we call ionization energies and electron affinities, so the tendency for electrons to either gain or lose electrons. On Monday when we get back, everybody have a great weekend, and text me or DM or email if you have any further questions.